Welcome everyone to 7.2 trigonometric integrals. Now in this section we have two main goals. The first is to identify strategies for actually integrating more complicated trigonometric integrals. We won't be able to get necessarily all of them, but we will be able to get a good combination of these things. And then the second thing is actually apply this. We will integrate some integrals. So let's get to it. All right, so in this first theorem, we want to integrate sine to some power times cosine to some power. And we're going to break it down into three parts. So the first part is going to be if cosine has an odd power. Second part will be if sine has an odd power. And then the third part will be, well, if neither of them are odd. And this will be the worst case scenario. When one of them's odd, that's a little bit nicer. Okay, so the claim is, in this first case, if cosine is odd, we want to use u substitution, really, but with u is equal to sine of x. So therefore, if u is equal to sine of x, then du is going to be equal to cosine of x. So therefore, it makes sense that we want to save one of these cosine factors, so that way it can be eaten up by our du. The rest of them we're going to turn into sines, and we're going to use this identity, cosine squared of x is equal to 1 minus sine squared of x. So, therefore, right, if we have this as an odd power, 2k plus 1, we're going to write it as, well, we're leaving all the signs as sines. So sine to the m of x. We're going to group the rest of them, cosine squared to the kth power, times cosine of x dx. So we're leaving just one of them to be eaten by this du. So therefore, we're going to have the integral of sine of x to the nth power, and then all of those cosine squareds we're going to be turning into 1 minus sine squareds. And there's k of them. All right, so that's going to be the strategy for the first case. In the second case, when we have sine being an odd power, it's going to be very similar, right? So in this case, we're going to let u be cosine of x. And then du is going to be negative sine of x dx. So we're going to try to save one sine factor to be used up by this du. The rest of them we're going to turn into cosines via the identity sine squared x is equal to 1 minus cosine squared x. So therefore, again, sine we're assuming to be odd here. We're going to leave one of them to be eaten by this dx, and the rest of them we're going to turn into cosines. So we're going to group them as sine squared of x to the kth power, leave all the cosines alone, and then this one, well, really, it's going to become like a negative du. That's fine. So we're going to have the integral of, instead of sine squared, I'm going to write 1 minus cosine squared. There's k of them. And then there's n cosines, one sine left over, and a dx. Okay, so let's take the strategy and actually apply it to see how we use this. So in our problem, we can see that cosine, there are three of them, right? So in this case, we're kind of in this first scenario. So sine of x is going to be our u, and then du is going to be cosine of x. So we're going to try to keep one of the cosines and turn all the others into sines, so that way they can be used as u's. So sine to the fourth of x times cosine squared x times cosine of x dx. So we're breaking off one of them. And now we can see that's going to be my du. So this is going to be u to the fourth times, and I'm just going to keep it as cosine squared for a second more, and then this cosine of x dx is going to be my du. So now all of those cosine squareds, in this case there's only one cosine squared, I'm going to transform into 1 minus sine squared. So 1 minus sine squared du, and of course we know that sine is u. So I can write this as u to the fourth times 1 minus u squared du. And now we've done the hard part. We've applied the strategy, now we're back in Calc 1 world. Right, so let's just evaluate this as we would in Calc 1. Distribute the u to the fourth, and then integrate, so I get 1/5 u to the fifth minus 1/7 u to the seventh, plus my constant of integration. Then substitute back in, well, everywhere I see a u, I'm going to put sine. So 1/5 sine to the fifth of x minus 1/7 sine to the seventh of x, plus my constant of integration, bada bing, bada boom. And there's our final answer. Okay, so let's get on to our third type of scenario here for when we are integrating a power of sine times a power of cosine. And that is if they're both even. So if we can't pull off this trick, then the claim is we want to use some of these half-angle identities. And we've rewritten these half-angle identities. You can actually look them up online. They're called power reduction formulas, right? So they're a way to take sine squared or cosine squared and reduce their power. Okay? So the claim is if you rewrite the half-angle identities, which we know and love from trig, we can write them as 1/2 times 1 minus cosine of 2x in the case of sine squared. And in the case of cosine squared, we can write this as 1/2 times the quantity 1 plus cosine of 2x. So it's just the difference between the plus and the minus here. And then sometimes it's also useful to know that sine of x times cosine of x is equal to 1/2 sine of 2x. And this we can get from the half-angle identity for sine. Okay, so now I have an example for us, and we'll do this in two different ways, actually. It's sine squared times cosine squared of x dx. That's the thing that we want to integrate. So in this first case, I'm going to look at this as sine squared of x. So I'm going to substitute in with my new half-angle identity here, or power reduction formula if you like. And then cosine squared, again, I will substitute in with my identity. Let's see, there's 2 halves, so I can kind of factor these out, and I'm going to get 1/4. And now we need to expand this out. Oops, I forgot my dx. So 1/4, and if we expand this out, well, this is like a difference of squares. So a difference of squares, or if you FOIL it out, either way, you'll get 1 minus cosine squared of 2x dx. So then the claim is, well, let's use the power reduction formula, or this half-angle identity idea, a second time, because I still don't know how to integrate cosine squared. So instead of cosine squared, I can substitute this as 1/2 times 1 plus cosine of 2x, right? Because I already had 2x, and I need to multiply that by 2. So that's the same thing as cosine of 4x. All right, so now let's simplify down a little bit more. So let's see, this is going to be, if I integrate 1, I'm going to get x, and I'll distribute this fourth along. All right, I have 1/2. Oops, 1/2 times 1/4 is 1/8. When I integrate that, I get x. And then when I integrate the cosine, I'm going to get sine 4x divided by 4. And it looks like I forgot my constant. So I'm going to have a negative 1/2 and a 1/4. So that's going to be negative 1/8. Hooah. All right. So now let's simplify one last time, right? So this is when I got all the distributing here. 1/4 times negative 1/2. That's gave me the negative 1/8. So let's do one more simplification here. So this is 1/4 minus 1/8 is going to be 1/8 x, and then minus sine of 4x divided by 32, right? Because 4 times 8 is 32. All right. So there's my final answer, and I wanted to do this in a second way, so an alternative way, which I personally think is a little bit faster, and that's going to be using this sine x cosine x rule here. So notice that we can think of this as sine x times cosine x quantity squared dx. So if I apply this twice, I'm going to get 1/2 sine of 2x, that quantity squared. So when I square that, I'm going to get 1/4 sine squared of 2x. And now I can use my sine identity. Right, so this is going to be 1/4, and then my sine identity says that this is going to be, let's see here, 1/2 times the quantity 1 minus cosine of 2x. 2x, that's the same thing as 4x dx. So now let's go ahead, I'll expand this time before I integrate. So this is going to be 1/8 minus 1/8 cosine of 4x dx. And now we integrate, and when I integrate 1/8, I get 1/8 x, or if you'd like, x over 8. And then I get minus 1/8, and when I integrate cosine, I get sine of 4x, and then chain rule says I would need a 4 on bottom. So this is going to be x over 8 minus 1/32 sine of 4x. Now let me go ahead and highlight these, and we can see that either way we get the same answer. So like I said, it's sometimes helpful to know the identity. I think this was a little bit faster, but it's not necessary to remember it, but it is nice. Oh, and I forgot my plus c's, so there we go. Okay, so let's go ahead and finish up maybe one more page of notes, and then we'll take a break here. So I want to go over strategy for integrating tangent to a power times secant to a power. And again, we're going to break this up into a few cases. So the first case is if secant is even, have an even power. And then the second case is going to be if tangent is odd. So those will be my two cases here. So if secant is even, we're going to substitute in u as tangent of x. So therefore du is going to be secant squared x dx. So we're going to save one factor of secant squared to be used by my du. And then the rest of the secants we're going to transform into tangents. And we're going to use the identity secant squared x is equal to 1 plus tangent squared x. So therefore, we can transform our integral into the integral of tangent to the m of x times secant squared x to the k minus 1 times secant squared x dx. And then finally, we can write this as tangent, right? So the integral of tangent to the m of x, and then we're going to transform these k minus 1 secant squareds into 1 plus tangent squareds. And then again, we leave 1 secant squared x dx to be used by my du. The other case that we'll go over is how do we integrate when we have tangent to an odd power. So in this case, we're going to try to save, we'll use u as secant of x, and therefore we want to save a secant of x times tangent of x dx. And that'll be used by my du. So we want to save one of these factors, and then the rest of them we want to be used by secants, right? So we're going to transform tangent squared x is equal to secant squared x minus 1. So in this case, we'll have the integral of tangent squared x to the kth power times secant to the n minus 1 power of x times secant of x, right? Because we're just taking one of them, and we're using one of our tangents for our du. So then let me cheat here because I'm running out of room. So I'm going to just move this over. The idea is that then we're going to use all of these right here, all of my tangent squareds, and I'm going to transform them into secant squared x minus 1s. So erase and secant squared x minus 1. Okay, so again, I think this is kind of confusing. This is the strategy for the general form, but let's use something concrete. Let's do an example. So I have tangent to the 4th of x times secant to the 6th of x dx, and I have to decide which kind of situation am I in. It looks like I'm in the first. So secant is even here. So in this case, my idea is that I want to keep a secant squared around, one secant squared to be used by my du, and the rest of them I'm going to turn into u's, so tangent of x. So u is tangent of x, du is secant squared. And so let me go ahead and rewrite the integral. So tangent is u, so u to the 4th times, let's see, I want to use 2 of them to make my du, so that means I'm going to have 4 left over. So that's going to be secant to the 4th of x. And now I want to take those and I want to transform them into tangents, right? So in order to transform them into tangents, there's my formula. Secant squared is 1 plus tangent squared of x. So let me go ahead and rewrite this as secant squared of x squared du. Okay, and let's pause really quick. Let's say we don't remember the formula. Let's do a quick way to how do we recall the formula. So the claim is that if you just remember sine squared of x plus cosine squared x equals 1, then we can divide through by cosine squared. And when you divide through by cosine squared, well, sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is just 1. And then 1 divided by cosine squared, well, that's secant squared. So this is the quick, easy way to remember, okay, it's secant squared of x is equal to tangent squared of x plus 1. So u to the fourth times tangent squared x plus 1. That quantity is squared times du. And now, well, tangent was the same thing as u. So I can write this as u squared plus 1 quantity squared times du. So now I need to FOIL this out, right? And we have to FOIL it out carefully. So let's see, u to the fourth plus 2u squared plus 1. And you have to remember you can't just distribute that squared, right? If you were to just distribute that squared, you'd get to the u to the fourth part and you'd get the 1 part, but you'd miss this 2u squared. So you have to actually FOIL. That's a common mistake there. Okay, so now let's go ahead and, right, we're safely in Calc 1 world. Let's go ahead and distribute this u to the fourth. And now we just need to integrate. So I get 1/9 u to the 9th plus 2/7 u to the 7th plus 1/5 u to the 5th plus my constant of integration. And resubstituting back in tangent, 1/9 tangent to the 9th of x plus 2/7 tangent of x to the 7th plus 1/5 tangent of x to the 5th plus my constant of integration. All right, I think that's probably a good place to stop. Let's go ahead and stretch our legs, and then when we come back, we'll do a few more examples. See you soon.